yourself and sharing your book with us. And as usual, Panos, I didn't really ask you, but we like to give a book prize. We'll pay for a copy of your book or two and give a prize to someone that asked you maybe the hardest question or the most interesting question. So if we could ask you just to think about that, and then at the end, if you could then just help us decide who that lucky prize winner would be, and then we'll go from there. But Panos, really looking forward to the presentation on what the large language models can do and conceptual modeling. Look forward to it. We've had a few people talk to us, so it's going to be interesting to see what your presentation is all about. Thank you.
Thank you. Thank you for the invitation, for addressing this community. Yeah, let me start. So I'll try to share my screen. Okay.
Amazing, we can see it.
Okay, great. Okay, so yeah, my name is Panos Alexopoulos. I'm from Greece, and currently, for the last actually 8 years, I live in Amsterdam, in the Netherlands. And the way I describe myself professionally is nowadays is like data and AI practitioner and educator, whatever AI might mean. This is a very big discussion. And yeah, today's topic, as Howard said, is about the interplay, the relation between knowledge graphs and semantic models and conceptual models in general with the new kid on the block, large language models. And particularly on how large language models can, what roles they can play in knowledge graph development, and how well or how bad they are in these roles. So a bit of background on me. I've been working since around 2006 as an ontologist in the field of data semantics and NLP AI, both in research and academia. And for the last 8 years, I work in a Dutch company called TextKernel as head of ontology. TextKernel, to give you some context, is a company that builds software for analyzing and matching people's profiles, CVs, resumes, etc., with job vacancies. And we do that in multi-domain and multilingual and cross-lingual fashion. My team is responsible for developing and maintaining a large knowledge graph about concepts and entities and related to recruitment, related to HR functions. And this knowledge graph, along with, in combination with advanced machine learning techniques and algorithms, enable the magic behind our services. Also, since 2018 around, I have started developing and delivering courses for professionals, mainly in the fields of data semantics and NLP and AI. And in 2020, so it's not so new anymore, after actually having several frustrations with with the field of semantic modeling, I decided to write a book and complain formally about that. So this is a book that tackles the general notion of semantic modeling, so not only ontologies, not only metadata, but rather a bit more generic aspect of semantic representation of data. And the main focus is on giving, how to say, practical advice on how to avoid pitfalls, as I'll call them, and also break dilemmas. So what do I mean by semantic data modeling, right? Because this is, it's, you know, we ontologists, our whole goal is to define terms. So I'll try to define what I mean by semantic data modeling. So this term is actually an umbrella term, an umbrella concept that involves, that actually describes the practice of developing descriptions and representations of data that convey the data's meaning in a way that is accurate, explicit, and commonly understood and accepted way among humans and systems. In other words, I perceive my interpretation about data modeling and semantic data modeling in particular is about closing gaps in meaning across teams, across people, across organizations. How we do that? As I said, by describing data, by representing data, and that involves, and there is not a single way that this can be done. There are several artifacts that can be considered semantic data models. Examples being taxonomies of entities, taxonomies of terms, thesauri, ontologies, vocabularies, and nowadays knowledge graphs. Even entity relationship models from like 30, 40 years ago, you know, with yeah, sorry, are actually can be considered as semantic data models, exactly because their function is to convey data meaning. Knowledge graphs is an old new thing. What do I mean by that? Knowledge graphs are quite hyped for the last 10 years or so, actually since Google coined the term in 2012. But they're really not something new. They're actually a rebranding of terms like semantic networks, knowledge bases. Some of you might remember this from the 80s and the 90s. Ontologies, linked data. So the definition that I like to give is that knowledge graphs are interconnected entities under shared semantics. Right. So the idea is that in a knowledge graph, we describe the world, we describe a domain, we describe our data in an entity and concept-centric way. Right? It's not about rows in tables. It's not about JSON, XML, things like that. It's about entities and their characteristics and the relations between. And most of the people who I speak to, and I think the majority of IT and data professionals that have been working with database schemas, taxonomies, ontologies, or any other types of structured data, I do think that they already know a lot about knowledge graph. What is almost always under-communicated and under-stressed is the need for shared semantic shareability. Right, so I've been in conversations where we talk about, yeah, is it a graph database? Should we represent it as a graph? Should we represent it as XML? Should we represent it in a relational database? Forgetting, or at least leaving as an afterthought, what we put there, the content, how we describe the data, how we describe a domain, and whether our descriptions can be understood by other humans and systems, and whether that understanding is shared, we agree on the meaning of things. As I said, perhaps the most characteristic example of a knowledge graph is Google's knowledge graph, which everybody sees, but maybe they don't realize that it's a knowledge graph. So nowadays, if you go to Google and you search about an entity, Microsoft, for example, Dama, South Africa, Panos Alexopoulos, etc., along with any web page and online document that may be related to that, you also get a knowledge card on the right. So in this case, you see that you get information about Microsoft Corporation, which is an entity, and you get structured information about it in the form of relations and with other entities and attributes. So, for instance, the CEO of Microsoft Corporation is Satya Nadella, which is another entity. If you click on it, you will see Satya Nadella's knowledge card as well. Apart from Google, we also have nowadays a lot of organizations that build knowledge graphs, both private and public and governmental. A characteristic example is Bloomberg. Bloomberg is a financial services company, financial data service company. So their goal is, their mission is to provide actionable data to investors and to other financial professionals. And something that they have been building for the last years is a knowledge graph that encodes knowledge about companies, about industries, about people, about geographical locations, products, financial instruments, etc. Right? And it's a graph. It's a knowledge graph in the sense that, as you see, it has concepts, it has relations, etc. And even though it's a new, I said it's an old term. At some point, it became a hype. Nowadays, it's not so much of a hype because if you're familiar with the Gartner hype cycle, in last year it was positioned by Gartner in what is called trough of disillusionment. So it's like it has reached the peak of inflated expectations. We know what this technology can and cannot do. Actually, it's more an approach rather than a technology. And nowadays, we find it to be quite practical, with of course its pros and cons when dealing with data. Now, why we build knowledge graphs, right? Beyond what they are. There are many applications that we use them for, but in an abstract way, in a generic way, we have three high-level usages of knowledge graph. The first and foremost is we use a knowledge graph as a semantic layer on top of, as a common semantic layer on top of heterogeneous data. Where in an organization, we have a lot of data silos, we have one team has a relational database, another team has XML files, another third team has a data warehouse, another product uses something else. Our whole goal is to integrate this data into a semantic way, into a common way, under a common understanding, so that we are able to access them in a homogeneous way, which is a difficult process. Right? It's not something that you achieve like in a month or even in a year, right? It all depends on the complexity, but the approach of a knowledge graph, the idea of a knowledge graph, is the main means by which you do that. You start with your data pieces, you add semantic descriptions, and you start gluing things together. When you have glued things together,
Sorry, Panos. Could I ask, I'm hoping, can I ask a question now or should I wait until later?
Yeah, you can ask a question now, yeah.
Okay. So is this something that I think Dave McComb was talking about in terms of almost that virtual layer or a semantic layer on top of all of your data that one could use as an API to access your data wherever it is, and then it transforms it from whether it's on a mainframe or in a database, or transform it to a logical model or something that's understandable to you?
Yes, exactly. It's more or less the same in an abstract way. It's the same. It's the same notion. The knowledge graph is a way to implement a semantic layer. There are other ways, but this is one way.
Okay.
Indeed.
Thank you. Thank you.
So when you have glued all your information and you have your layer, then you are able to perform data analytics and data science algorithms and other operations, question answering, things like that, on top of this. So instead of, for example, let's say you have a question about something, and this question can be answered by combining information from different silos, from different databases. By having the semantic layer, you ask the question to the semantic layer, and then the semantic layer, the knowledge graph, will give you the answer, which has already been combined from the other sources. And if done correctly, right, this gives much more value, much more accuracy, actually, to the insights that you get from your data, right? Because the whole effort of integrating the data in a semantic way actually results, again, if you do it correctly and properly, results into a higher quality of data. A third usage is the utilization of knowledge graphs to complement and enhance machine learning applications, right? So both in Taxiana and in many other cases, we have seen that just using a machine learning based, for example, classifier or information extractor or some other application is many times not enough. It's not enough because the data that has been used for training this machine learning application do not contain the domain knowledge that we need, or the algorithms that we use are not able to capture important facts and structure knowledge that everybody knows perhaps in the company, but it's not expressed in the data. So in such cases, using a knowledge graph, using a top-down approach of telling a machine what it should know, can help a lot, right? It's practically combining encyclopedic knowledge, right, declarative knowledge, which is a knowledge graph, with inductive knowledge that a machine learning system learns. Furthermore, one big problem that machine learning approaches have is the famous black box problem, right? They are rarely interpretable. We really don't know why a machine learning system has taken a particular decision. And also, when we try to troubleshoot a machine learning application, we're not able to go easily and fix something immediately. With knowledge graphs, this and with symbolic AI in general, this problem can be partially alleviated. We can use knowledge graph to provide explanations for why something happened, for why a system has behaved in a particular way, and we can use it to go and fix things much easier.
And Panos, is this also a situation where if it comes up with something that is against what the semantic meaning is in the knowledge graph, could it then detect whether this is not good quality or in terms of extrapolation, or maybe we need to enhance the knowledge graph?
Yeah, indeed. So you can use, for example, by having in the knowledge graph explicit, for example, constraints or things that you know they are true, you can control the output of a system, of the machine learning system. So let's say that you generate facts from, for example, you use a large language model, you get something that is not consistent to what the knowledge graph says, then you are able to mitigate the problems of the machine learning, of the model. Yeah.
So we can address those hallucinations where we can say this.
Yes. To some extent, yes, exactly. We're not going to talk a lot about this today, but I will give you links. I'm also covering this to some extent. Yeah.
Okay. Okay. Thank you.
Okay. So I repeat, like I like to repeat always in my talks and in my courses, the crucial dimension of the graph, beyond discussing about if it's RDF, if it's, if we use RDF or if we use property graphs, if they're big or small, if what domains they should be, is about three things. It's about meaning accuracy. We want the meaning of each entity relation or other element we have in the knowledge graph to be correct and accurate. So we don't want wrong facts, right? Because again, it's like garbage in, garbage out. If we put bad knowledge in the knowledge graph, we get the same problems that we also get with bad machine learning. The second thing is that the meaning should be explicit, right? Yes, we want, usually these artifacts are to be used, of course, by machines. So in that case, we can encode everything with IDs, etc. But ultimately, the names that we use for our entities, the names that we use for our relations, the descriptions, the definitions, etc., should be such that any human user of a semantic artifact and of a knowledge graph can understand what they're about, right? At least within the domain that we're covering. And the third dimension is agreement. How commonly acceptable is the meaning of each entity and relation among the people and systems that use the graph? Give you an example of problematic agreement, for example, is in our field of recruitment and of professions. Some years ago, we were considering if we could reuse a knowledge graph that the European Commission had built about professions. And as we were inspecting the data, the knowledge, we realized that in many cases they consider various professions to be equivalent, so to be synonyms practically, that for many of our clients and for many of our domain experts were not. So for instance, they had under the same entity, under the same concept, the notion of a data engineer and a data scientist, which in the majority of the job vacancies that we see on the profiles, these are completely different things. Not completely, they're very different things, right? So what does that mean? It's not that they were necessarily wrong, but it's we didn't agree with their definition of data scientist, data analyst, right? And this agreement, I mean, when you build a knowledge graph or when you build an ontology, your goal and our goal is not necessarily to reach a global agreement that can take forever and may never happen, but you need to have a defined scope of intended agreement, right?
Yeah.
So are you building your knowledge graph just for your team? Fine. Are you building it for the whole organization? Are you building it for a geographical location? How many users? So usually you have to define a scope. The bigger is the scope and the more heterogeneous is the scope, the more difficult will be to achieve agreement, unfortunately. Accuracy is not so much of an issue, but exclusiveness and agreement, it's more difficult. And that makes it even more challenging. And the enemies that, as I like to call for this, are various linguistic and semantic phenomena that we have in our human language and communication. We have the problem of ambiguity, right? People use the same terms to denote different concepts, right? Plant, for example. We have the inverse problem. We have, again, humans using, in human language, using different words, different terms for the same concept, right? Someone might say, for example, you know, I really like the city of light. Which is the city of light? That's Paris, okay? Right? So you see that in a text, you need to be able to understand that city of light there refers to Paris in France, for example, and not Paris in the US. So that means that your knowledge graph, if it's to properly have properly model the semantics of a domain, needs to capture explicitly the ambiguity that exists. So for every term in your domain, it needs to have all the possible meanings that are important for you, and vice versa. For every important concept, the most typical ways that these concepts can be expressed by your users who may be using, you know, to ask questions, or in the text that you are analyzing, for example, if you're using or in the data that you have. A third big problem, which is very characteristic of human, again, thinking actually, is vagueness. Vagueness is when you have concepts, when you have predicates that do not have unique truth criteria. So if I ask you, can you give me a definition of a tall person? You are not able, there's no universal definition of the threshold of height, the exact height that separates tall people and non-tall people. The same can be said for many other predicates like large, critical, poor, which we use actually in our education, right? So because of that, vagueness causes a lot of disagreements. It's actually the arch enemy of meaning agreement. It's the same problem that we have when we discuss with clients and say, what is the definition of a data scientist? What does it involve? How can you tell? You have people saying, no, what this job vacancy is not about a data scientist because, for example, it doesn't talk about statistics. Okay, is statistics an essential skill for a data scientist? Sometimes yes, sometimes no. So that's actually our everyday job as conceptual modelers, as ontologies, as semantic and data modelers. A fourth problem is semantic change. The meaning of things change. In some domains are very volatile. You have new concepts, new ideas very frequently. Others change rarely, but still you need to capture that. So if you build a knowledge graph about the domain now, it may be that in 5 years from now or in 10 years from now, many of the concepts will have a different meaning, or at least a slightly different meaning, which also means that these artifacts are not static and are not meant to be static. It's not like sometimes I get requests saying, can you build me a knowledge graph? I said, yes, I can build you a knowledge graph version 1 in 5 months, 1 year, yes, but then you have to maintain it. If you don't properly maintain it, especially if your domain is highly volatile, whatever benefit you will have will diminish faster or slower, but it will diminish definitely. A fifth problem is more to our control, is suboptimal development practices, and mostly different development practices, right? So you have teams of data modelers, of knowledge graph developers that may be using different techniques, different methodologies that result into different artifacts. They may be doing something that is wrong. One thing may be doing something that is not completely correct. Okay, that's relatively easy to see, but they also have been. They may have been following different approaches for the same problem, also legitimate, but because of that, there is a big issue on merging things, on aligning things. And this actually, fifth aspect is something that I try through my book and through my talks and courses to, let's say, reconcile to some extent.
So sorry, Panos.
Yeah.
I attended a conference in 2019, and I was very surprised. We had several presentations on ontologies, and in talking to one person, they felt that the other ontology that was developed, I don't want to mention names now, was very bad. It wasn't it wasn't well developed in terms of the structure and elements like that. And it almost rendered all of that work that had been done for close on 3-4 years, as far as the lady was concerned, she felt it was useless. The the ontology was useless. Is that what there seems to be not a standardized approach to these developments, and so you can come up with very different graphs or ontologies.
Right. So first of all, I think the term useless for a project of 3 to 4 or 5 years is a bit, it's like hyperbole, right? It's not about useless. It may be that if you come and check, let's say, if I show you the ontology and knowledge graph that we have in my company, right, and you evaluate it, you will find many problems.
Yeah.
But the thing is not so much the problems you find, is how much the problems you find affect the end application that you want it for.
Right.
So, because ultimately, when you have limited resources, you have to prioritize.
Right.
I say in my book somewhere, I have several dilemmas about the content and about the practice. For example, one usual trade-off is completeness versus precision versus accuracy. Right? If I want to have millions of entities in my knowledge graph, I cannot scale that humanly. I cannot have domain experts do that. So I need to utilize information extraction processing, natural language processing, machine learning, which knowingly have a level of precision, a level of accuracy, and 70%, 50%. And then we have some humans in the loop, for example, that's a common thing, that will take a sample and try to check the quality and fix things, but you cannot fix everything. Right?
Yeah.
So it's not that it's useless. And when I said about the case of the European Commission's project, I didn't say that's useless, but when we saw it, we saw that it was different. And
yes.
we judged that for us, it didn't fit in our case. But that doesn't mean that it's not used by others and that it doesn't provide value. That's a difference.
Okay. Thank you. And we've got another question. Marcel has a question. Yes, Marcel?
Thanks, Howard. I recognize these as real enemies, especially in our environment. So I might be preempting, but are you going to talk how to address these enemies? Because they are very real, and we seem to have these challenges with these enemies on a daily basis.
Yeah.
Thanks.
Yeah. So first of all, I put them in quotes because it's not about its enemies, but it's not about eliminating them. You cannot eliminate ambiguity. You cannot eliminate vagueness, right? they're there. It's about addressing them and managing them and handling them.
Yeah.
In a bad way. And of course, now in 45 minutes, when we're not able to talk about each of these, how to do it, right? About the bigger things. But this is what exactly I'm trying to address in in my book, but also in my courses. So, for example, I have a dedicated module on what do we, when we model, when we create a model, how would we even, first of all, how we start by detecting vagueness? Because one, at least for the semantic web community and the ontology community, vagueness is almost a forbidden word. They don't use it. Everything is Boolean for them. Everything is Boolean for them. Nobody talks about that. So I start first by addressing the elephant in the room, and then having some techniques. But yeah.
So with a lot of collaboration.
Yes. There is the thing is, data modeling is not an engineering, in my view, it's not an engineering challenge. It's a people's challenge.
Exactly.
And we will see that even with the large language models that are supposed to capture the way people talk, express themselves, there are many problems. Maybe in, I don't know, in 5, 10 years, I don't know, 20, we will have AI that will understand everything. We will not need that. But for the time being, the job of a data model is practically deciphering what people say and what they mean. That's my view. It's not about the language, the framework that you use, or the algorithms that you write. That's the main thing. Okay. So because of that, as I said, search semantics in a large scale can be hard, right? And since the large language models have gotten out, sometimes or many times in conferences and people that I talk to, they say, okay, can I just stop developing knowledge graphs and let's use directly a large language model for that purpose? Okay. In order to think of that, let's first start with what a large language model is. So a large language model is a machine learning model that has been using an architecture called transformers. Doesn't matter so much the details here. And it's practically a machine learning system that has been trained on massive data sets of text from the internet with the goal of generating human-like text. And let's say as a side effect of that, to show that it understands human-like text. But its main goal is, when it's being trained, is to be able to complete actually our phrases, to generate more text given an input text. When these models were first released, they really surprised people, mainly because of their fluency rather than the content. And they're nowadays considered as useful for, at least they're being investigated for being used for natural language related tasks: text generation, text classification, sentiment analysis, summarization, many tasks. And one main feature that they have, to which I think they owe their popularity more than the quality of their output, is the simplicity of their input. Whereas with a knowledge graph, with an API, with previous technologies, you had to have a certain level of technical knowledge in order to create these models and use them. For the average user of an LLM, things are quite simple. You just write in natural language, what do you want the LLM to do? And it will give you some output, right? This is the famous LLM prompt, from which actually the last, even within a year and a half now, a very, let's say, a large part of a large body of content has been generated about how to do what we call prompt engineering, how to write, the do's and don'ts for writing good prompts for making the LLM do what you want it to do. And my personal view still is that prompt engineering is more like alchemy and has nothing to do neither with science. It's what seems to be working. Okay, that's fine. Heuristics are always part of engineering, and I'm okay with that. But it's not like the advice of that you get. There's no, how to say, it's not certain that it will be valid for other large language models, or that they are based on solid foundational scientific facts and findings from the past. That is an issue there. But we are engineers, we are pragmatic, so it's not about so much the science here, it's about whether they can do what we want them to do, at least for now. The main issue with using an LLM as instead of a knowledge graph is that LLMs are usually really bad knowledge providers, right? LLMs were never designed for the task of information retrieval, nor for search as a search engine, nor for retrieving data from a database or a data warehouse. They're designed to generate probabilistic text, and for that they have, I think someone mentioned already, the problem of hallucination. So you ask them something, they will give you an answer. You cannot be sure that the answer is correct. Here is an example. I will analyze further this example later, but some time ago, I asked ChatGPT, give me a list of books that have been published by O'Reilly publisher about data engineering. It gave me 10 books, and the first book is actually a real book. It has been published. The author is correct. O'Reilly is the publisher. But then you have something like Data Engineering Tips by Jesse Anderson, the second book, which is the author is correct. The title is not correct, and definitely the publisher is not correct. And same as others, same as the others. So LLMs are very different from knowledge graphs, and there are strengths and weaknesses, cons and pros in each of them. With a knowledge graph, what you get is structural explicit knowledge. You have symbols, right? You see a concept, you have a description, you understand what it is about. If it's not well described, you may not understand it very well, but still you get a term, you get a word. With an LLM, what is in the LLM is just numbers, right? They are weights, they are called embeddings usually, but they are just weights in a massive neural network. So you don't really know what's going on in there. The only way you can understand, you might get a glimpse of what the LLM knows is by asking it. And then the problem comes that when you ask it, it might make up things, right? It may tell you things that are indeed correct, but it also may just make up things. Whereas a knowledge graph just will give you what it knows. If it's incorrect, the problem is not of the knowledge graph. The problem is the responsibility is whoever put the knowledge in the knowledge graph, right? It's not the artifact of the knowledge graph that will make. It's not the structure of the knowledge graph that will create the inaccuracy. It's the actual content. Whereas in the LLM, the problem is the inference that the LLM does in most of the cases, along, of course, with the content.
Sorry, Panos.
Yeah.
Sorry. So are you saying that because the knowledge graph will consist of two parts? One is the ontology, and then it's the instance data that's loaded into the graph, and then the association between the ontology and the node. Are you saying it's that ingestion and the association to the ontology that's wrong?
So in a knowledge graph, you can have the mistakes that you can be related to the connection of the data with your ontology.
Right.
For example, you have the concept of customer, right, of your companies, and you have people or organizations that are not really customers. But you might also have conceptual errors, like, for example, saying that a data scientist and a data engineer are the same thing. Right? So there can be many issues in the knowledge graph. The thing is that whatever problem is in the knowledge graph, it's not because of its structure, it's because of its content. That's what I'm saying. It's not because of the way you use it for inference.
Okay. All right.
And in a knowledge graph and in an ontology, the kind of reasoning you do is only deductive. Deductive means that you have a rule, you have something that is true, and if the rule, if the premise is true and the rule, of course, is correct, what you get is definitely correct. Whereas it's always correct, right? All humans are mortal. Socrates is a human, therefore Socrates is mortal. This is what we call deductive reasoning. In an LLM, the reasoning is not deductive always. Many cases, it's actually inductive or abductive. It has an explanation. So the answer that you get might be correct with some confidence, but it's not. There's no guarantee that it is correct. And LLMs, exactly because of that, are black boxes. It's very hard to interpret. Whereas with a knowledge graph, you can actually go and see what it contains. On the other hand, knowledge graphs are very bad with language. They are optimized for conceptual knowledge, for facts, but not for understanding language. One big application that we see now with LLMs is question answering, natural language question answering. What is that? You don't want to write an SQL question to your data. You want your users to be able to just write a natural language question. Tell me, what are my customers, for example? The translation of a natural language question to a structured query, SQL, Sparkle, Cypher, etc., before LLMs, and actually it used to be very difficult. It's still challenging, but it has become slightly easier now, because LLMs have managed to capture a lot of linguistic patterns that we use in our everyday communication, and these linguistic patterns can be very useful when interpreting text, natural language. So we see that the LLMs cannot really replace knowledge graphs. And we also saw that knowledge graphs can be really hard to develop and scale depending on the domain, depending on the scope. So the next question is, can we use an LLM as an assistant to automate and scale the development of the knowledge graph? So here is the topic of this talk. Based on what we've seen in this past, my team and also other people that I've been talking to, we have seen three main roles that an LLM can play when we develop a knowledge graph. The first role is to use an LLM as a direct source of factual and domain knowledge, so as a domain expert. You are building a knowledge graph about biology. You may be using the LLM to help you with facts and about biology. You are building a knowledge graph about the automotive industry. You may be using an LLM for that purpose. The second role, the second task, is what we call knowledge modeling or semantic modeling, which is the practice of taking requirements about knowledge representation, right, what the knowledge graph should contain, and transforming them into formal representations from the language that we use to represent the knowledge graph. If we use, for example, RDF and Ontology web language, we give an LLM in a natural language the questions that we want to model, and this provides us with the old code. Similarly for other things. So this is pretty similar to the use case of coding for software engineers, right? Which is, maybe you've seen a lot of posts in LinkedIn and elsewhere that they have been using LLMs to help with coding. You just say a function to do this in Python or in Java or in C++, and the LLM will give you that. The third usage is knowledge mining. This is when we use an LLM to extract information from text usually, and take these facts and add them to our knowledge graph. For example, we have a large corpus of scientific papers about biomedicine, and we want to that reflect scientific knowledge about biomedicine. We want to extract what is in there and get the entities that are there, get the relations between the entities, for example, between genes, between proteins, between these things, right? And put them in the knowledge graph in an as much as possible automatic way, right? Without the need for human input. So let's see now each role separately. First, LLMs as knowledge providers. I already shown the example of the book, but it can happen that in some cases an LLM can give you some rather correct things, right? Like here, give me a list of the EU countries. The issue is that, as I said, that an LLM might generate facts that were never in the data, nor can be deductively inferred. That immediately makes them unreliable. It's not that they will always give you, that they will always hallucinate, that they will always give you something wrong. But if you are not able to corroborate what you get from the LLM with some additional data source in order to check the validity of the correctness of the facts that you're getting, you're risking things. You are risking the accuracy of your extracted knowledge. And this hallucination problem is called hallucination, but it's like, I'm not sure if it's a correct term, but in any case, the issue is that the LLMs are designed to generate human-like text based on the patterns they have identified in vast amounts of data. The reason they hallucinate is because it's a mixture of overfitting and biases in the training data, and the models attempt to generalize from vast amounts of information, right? It's not, the LLM is not taught to take a fact and just retrieve that fact. It is taught to take this fact, take fact A, fact B, in natural language, and try to create a generation rule that based on that, this can happen. If the training is not good, or if the training data are not good, or they are conflicting, etc., then the generalization will not be good. Another issue with that I also found when as I was experimenting is the treatment of ambiguity from an LLM. So if you notice, if you try to make a question to an LLM that is ambiguous, for example, when was Roger Moore born? I never talked who Roger Moore is in this case, right? There are many Roger Moores in the world. Of course, your mind immediately goes perhaps to James Bond, to the British actor. And actually, this is the answer you get from ChatGPT. But the thing is that, how does it know that I meant that person? It really doesn't. It just, based on what it learned, it assumed that this was my question. Whereas a proper, if you use this, whereas a proper reply would be, okay, I have 4 Roger Moores in my knowledge. Which one do you mean? That's something that you would expect from a knowledge graph, where you would have 4 entities Roger Moore with different IDs and different relations, etc., and you would do something called disambiguation. Similarly, for another case, which is the director of movie Dune. And as I was playing and trying to see how can I make the LLM understand ambiguity, I started playing with trying to give it more further context, because the main issue is that the questions they gave did not have a lot of context. So I rephrased my question and I said, okay, look, you are a domain expert in cinema. I will ask you a number of questions about movies. If a question is ambiguous, ask me to clarify. So I'm practically give the LLM a warning. Look, the question might be ambiguous. It still had the same problem. So I'm like, okay, obviously didn't understand what ambiguity means. Let's try to make it even clearer. I'm rephrasing the question and I'm saying now, if a question refers to ambiguous entities, e.g. movie titles, person names, ask me to clarify. So instead of ambiguous question, I said ambiguous entity. So I try to make the notion of ambiguity even clearer, right? It's like explaining to a human, to a fellow moderator, the domain expert, what is ambiguity. Still problem. And I only managed it to work only when I gave a even better definition of ambiguity, saying that an entity is ambiguous if there are other entities in the same domain with the same name. Then and only then, when I asked who directed Dune, it identified several Dune versions, and therefore it asked me to clarify the question. So what does that mean? It means that left on its own, an LLM will not detect ambiguity in this case, and without adequate context, it will just give the answer it considers more likely. More importantly, it's obvious that from this example that the LLM does not really understand phenomena like ambiguity, phenomena like vagueness, etc. Right?
Mm.
Things that we know very well from analytical philosophy, from humanities, etc. For the LLM, this doesn't exist unless you try to teach it, unless you try to explain it to them. So, as a summary, for the LLM as a knowledge provider, what we may say is that an LLM might contain factual and domain knowledge. Actually, they always contain factual and domain knowledge, but it's not easily and reliably retrievable, always. So the advice here is use an LLM as a knowledge source for things you can either double check, in conjunction with other knowledge sources. For example, in TextKernel, what we do is that we may ask an LLM something, tell me, for example, what are the main skills for a particular profession, but then we will go and look for what it said in our own data, because we have a vast amount of job vacancies and professions. So if, for example, it says that an important skill for this profession is that skill, but we don't see that correlation at all in our CVs and vacancies. So no, for example, data science has this particular skill, or nobody in the job market asks for these skills, then we're not going to trust it. Whereas if we see it a lot there, then we know that most likely it's correct, right? So you need corroboration. You need to treat an LLM as an unreliable witness that may be saying something that is useful, but you need to double check. Now, let's go to the second role, LLM as knowledge modeling. Let's play it. I work with several languages. I work with mostly property graphs, but also semantic web languages. So I'm like, okay, let's see how well does an LLM, ChatGPT in this case, know about RDF and ontology web language. So I made a prompt that asked the LLM to transform competency questions into old code, into an old presentation. Competency questions is practically natural language questions that your semantic model, your knowledge graph needs to be able to answer structurally and content-wise. So it's a way to express requirements for what the knowledge graph should be look like. So I gave it these two questions. Tell me, who is the director of a movie? This is what I want your model to support. And who is the oldest actor of a movie? And actually, it went pretty well. So I'm not going to do the details now, but if you look this slide, you look at the code, it's actually, the modeling is quite correct. It defined classes like movie and director, a relation between movie and director was directed by, all fair and square, was good. But when I gave it a more tricky example, and I say tricky because I've been using this example, this quiz actually in my courses and also in the book, and I've seen that in 90% of the cases, human modelers make an error here. It also failed the LLM to deal with that. So the question is as follows. Tell me, I want to have two requirements. I want a model that can, where a company, we have companies that can have clients, and there are two types of clients, individuals and organizations. So what the system did, what the LLM said, it said, okay, I'm going to have a class client, fair enough. I'm going to have a class individual. I'm going to have a class organization, and I'm going to make, I'm going to have a relation, has client between a company and a client. And I'm going to make individual and organization a subclass of client. Now, this seems, I'd say, intuitive. But there's a catch here. The class organization, when you define it with that name, you expect it, when you see it on its own, you say, okay, this class models all the organizations. Whereas the requirement is that I want the organizations that are also clients, not all organizations. So an organization is not a type of client, because not all organizations are necessarily clients of my company. There are organizations that can be partners, that can be competitors, that can be other things. So this subclass, this is a typical misuse of the subclass problem, and it's also a typical use of wishful naming versus proper naming, because an experienced knowledge engineer here would say, I'm not going to call the organizational client's organization, I'm going to call them organizational client, which is a more accurate name of the intended meaning of that class. So the model here did not seem to grasp the formal semantics of subclass in the OWL, and it wasn't able to assign good names to the classes.
Sorry, Panos, there's
Yes.
a question from Marcel.
Yeah.
Marcel?
Yeah, maybe Howard, for both of you. I'm getting lost a little bit where glossaries and taxonomies play a role in defining the information that is used by the LLMs, and so how important is that? Because that is where your definitions and your logic are defined. So it must connect the client and the company that you're asking about, or the individuals and organizations. It has to be defined somewhere. So, and therefore your glossaries and your taxonomies need to be accurate so that it understands that information. Am I right?
Okay, so this is
where does the learning come from? Sorry.
Yeah. So okay, maybe I wasn't clear enough. Our goal in this case, we want to build an ontology that satisfies these following requirements, that is able to represent for our applications outside. Forget the LLM. Imagine that there's no LLM here, right? Yeah. So you are building an ontology, and you're getting the requirement by your stakeholders that, you know what, I want the ontology to be able to encode the following information, that our company, one company can have clients, which means that you need to create a concept of a company, concept of a client, and relate them, and that the clients can be two types, individuals and organizations. Before LLMs, before anything, and even now, you can just go, and this is actually the task of a semantic modeler. You need to take these requirements and create what is in the right, a formal representation. And what we're looking here is, can we, instead of we doing the thinking, can we ask the LLM by means of prompting to do the thinking for us and to help us and to produce the formal representation? We don't know what the LLM knows. We haven't trained. We just use it as is. And what we are looking here, what we are seeing here, that whereas in the previous example it worked quite well, in this case it did very important mistakes, because these are mistakes. So by that, we are inferring, right? At least, I mean, I know it's anecdotal, it's not a systematic evaluation, but it's evidence that the LLM is not really a superior knowledge modeler than most human data modelers yet. It's not something that you can also trust it fully for the task of getting knowledge representation requirements into formal knowledge representation.
So Marcel, if I could just, so the LLM has no concept of definitions, glossaries, and things like that. It's really just a set of numbers that understand almost how to generate the next set of words that Panos was talking about. Now, here it's really taking the prompt and using what we've provided in the prompt to generate the OWL code, and it actually, you know, it doesn't even worry about the definition. It's actually just taking what you've told it and then building the code and linking the organization. But because it doesn't understand the definition of the organization, it's getting these relationships wrong and calling them wrong. Does that make sense, Marcel?
Thanks a lot, Howard. Thanks, Panos.
maybe it knows, maybe somewhere from the data that it has been trained on, there is the definition, but it hasn't captured it, hasn't using it, right? It's
not using it. Yeah.
Here is another example. In taxonomies, in hierarchies, there is SKOS, it's called Simple Knowledge Organization System, and it's when you have a hierarchy of broader, narrower concepts.
Yeah.
Broader, narrower, usually, according to the definition, involves three types of relations: the instance of relation, the subclass of relation, but also the part of relation. So if we want to have a geographical hierarchy, like, for example, Greece is a location, Athens is in Greece, and Acropolis is in Athens, and we ask it to create this SKOS hierarchy, it's pretty correct, because it says that we have a concept Greece, we have the concept of Athens, which is narrower than Greece, correct, because it's part of Greece, and Acropolis, it's in Athens, it's part of Athens, so this is correct. But then, when we say translate this model into OWL now, it's the same thing, but not in SKOS, which has the broader narrow concept, but in OWL, which has even more formal semantics. So what's the problem here? It took and defined Greece, Athens, and Acropolis, which are individual entities, as classes, which is substantially wrong, because a class in semantic modeling is something that can have instances. Greece cannot have instances. There are specific examples of Greece. Athens does not have instances. There, the subclass of relation involves the part of relation, which actually is implied here. So also here, it wasn't able to do something very, very good. And here's another example. It's about meta modeling. I'm not going to cover it because we're almost out of time, but have a look in the slides. And again, the message is that the LLM does not seem to grab the formal semantics of all, nor to distinguish between classes and individuals. So overall, an LLM can help with knowledge graph modeling, but again, it doesn't necessarily understand the semantics of the modeling language.
Right.
It has seen a lot of examples of modeling from the data it has been trained on, some good, some bad, because there are bad examples, even in, remember earlier you said about the useless, again, I disagreed, but again, there can be, there are out there with ontologies and knowledge graphs with really conceptual problems, for classes as individuals, etc. And what the LLM has done is it has learned. Third role, LLMs as knowledge miners. Here, we have three main ways by which we can use an LLM to help us with information extraction. The first technique is called zero-shot learning. That is, we prompt the LLM without any examples of what we want to extract, attempting to take advantage of the reasoning patterns it has already learned. So for instance, we say to the LLM, this is the text, find me all the actors in that text, find me all the companies in that text, find me all the customers in that text. A bit more advanced is what we call few-shot learning. This is when we prompt the LLM with the same instructions, but in addition, we give it some good and bad examples of the task. Okay, I'm giving you this text, I want you to find me the actors. Here are some examples of correct actors, here are some examples of wrong actors. So it's a way with few examples to try to explain further the task. And the third approach, which is even more advanced and also more costly, is to take an existing off-the-shelf LLM, build our own data set with positive and negative examples for the extraction task, and fine-tune the LLM. What does fine-tuning mean? Fine-tuning means that we take the LLM, we don't retrain it from scratch, but we train it for some more iterations, which is cheaper, in order to adapt it to the particular task that we want. This is a very useful capability generally of deep learning of these models. Let's see some examples. Here is one. I have a text from a movie review, and I want to build a knowledge graph about movies, about films. So I take this text and I ask from the LLM to identify in that text all the actor, films, directors, and character entities. So what I expect, I want to, from this, to the LLM to tell me that, we have Al Pacino, who's an actor, we have The Godfather of 1972, which is a film, etc. When I ran this for the first time, I saw the result on the right, and I was like, okay, that looks good. But then I saw something that was slightly suspicious. If you notice, the second film is called The Godfather Part 2, 1974. However, in the text, it never says Godfather Part 2. It only says in Part 2, 1974. That's the fourth line. So how did the system know that Part 2 is the movie Godfather Part 2 and not something else? It's not in the text explicitly. So the suspicion I got there, it was like, okay, it's very likely that this is because the system conflates knowledge that it knows already from its training with what is in the text. In order to check that, I change the instruction and I say, you know what, do the same thing, but consider only what's in the text, not in what you know already. And in this case, in the films, it didn't say The Godfather Part 2, it only says Part 2, because this is what the text says, right? Again, I wasn't fully convinced. Okay, I saw that. I wasn't sure also about the others. So what I did is that I took a smaller text, and now I made my own text. And instead of saying that Godfather was directed by Francis Ford Coppola, I said the script of Godfather, written by Francis Ford Coppola, narrates the change, blah, blah. And I asked the system to tell me about actor, film, director, and character. So I still wanted the director. Now, according to the text, if someone who has no idea about this movie, from the text does not mention the director of the movie. It's Francis Ford Coppola, but the text only says that Francis Ford Coppola has written the scenario. And still, you see that the output is director Francis Ford Coppola. It shouldn't be there. And as a further example is when I changed the name of Francis Ford Coppola with John Doe, which is meaningless, then it actually understood that, you know what, we have no director information, so it didn't give me any director thing, but it gave me other writer John Doe. So in the previous example, it's obvious that when it saw Francis Ford Coppola, the name, it used the prior knowledge that it had about who is Francis Ford Coppola, etc., based on text that it has learned, and gave me something that wasn't in the text. So in an extraction task, the LLM will combine prior factual knowledge it has with information mentioned in the text. Sometimes that's desirable, and others is not. So it requires to be careful. I mean, it's not that it's not that I said this is wrong in the sense that I asked it what is in the text, but ultimately it was correct. So you need to consider your application, you need to consider your scenario to see if really this is something that is worthy or not, that's probably dangerous or not. Then I started playing with relation extraction. So the previous examples were entity extraction. And I said, okay, look, in this text, take this text and find me the relation between John Doe and Godfather. The possible relations are acted in, directed, wrote, and unknown. So I gave it as input and it brought me correct. It says, according to the text, the relation between John Doe and the Godfather is wrote. Okay. From previous experience with information extraction, I've seen that machine learning models many times that do relation extraction are not so good at handling phenomena like negation, like uncertainty, hedging, things like that, linguistic language phenomena. So I decided to try to confuse it.
Confuse it.
Yeah. And instead of saying the script of Godfather written by John Doe, I said there is the script of the Godfather rumored to have been written by John Doe. Right? So according to the semantics of written, I shouldn't get that the answer is wrote. I should get unknown. It might be, but we really don't know that. yet it still gave me the correct relation is wrote, which is wrong. And it's very funny that its explanation is also wrong. It's inference, because it actually says, yeah, it has room mode, so therefore the correct relation is wrong. And it only worked only when I gave it some examples. This is where few shot extraction came in. So I understood that the LLM doesn't really understand the notion of uncertainty. So I gave it some examples of positive and negative. For example, you see that the second example says Bill Dom might have written Toy Story, and the relation is unknown, which practically says, you know what, if you see might and things like that, you don't know really. And in this case, it worked. So an LLM can be a decent knowledge miner, but we need to provide it with very clear and detailed instruction examples, right? It's not like give me the entities, give me the relation, or build me a knowledge graph. This will most likely not work correctly. And of course, thoroughly evaluate it. Again, this is anecdotal here, right? But you need to treat this as a proper extraction. So evaluation data to see how well it does for different relations, for different semantic phenomena. Okay, reaching the end. 3 takeaways with respect to how good are LLMs knowledge graph developers. The first is that LLMs are rather unreliable knowledge providers. Use them carefully and in conjunction with other knowledge sources. As knowledge modelers, they're rather mediocre. They have learned the syntax of knowledge modeling languages from a lot of examples that they have been trained on, but they don't really understand the semantics. So use with cautions, and actually use them if, I would say, if in your team you have both experienced and non-experienced knowledge engineers and semantic modelers, don't give the LLMs to the junior ones, right? Or at least, have a way to double check that. Hoping the senior modelers, the more seasoned ones will find these things. It can be useful, right, to accelerate the modeling part, but it requires good inspection. So modelers it's the same with code, right? It's the same with software engineering. If you're a very experienced software engineer, you can see if it's you can see the issues, you can see the problems immediately. Finally, LLMs can be decent knowledge miners. They need very clear instruction and examples, but they need very careful evaluation, and they can become much better if they're fine-tuned and adapted for special tasks. At the moment, using an LLM for information extraction task can be an overkill in terms of cost, and in terms of speed many times, which means that sometimes using a more traditional approach for information extraction, either rules sometimes or some very basic entity extraction, relation extraction, can be much more efficient. But if we are to use LLMs, again, it's very important to have clear instructions, examples, etc. Okay, that concludes my talk. Before we go to further Q&A, I'd like to inform you about 2 upcoming courses that I have in this month and the next month. So if you're more interested in the interplay between knowledge graphs and large language models, starting next week, for the next 2 weeks, I'm doing with O'Reilly an online course on knowledge graphs and LLMs, 3 hours every week. If you are already a member of the O'Reilly platform, it's free for you. You can also, if you are not already a member, you can use a 10 days, a 10 days free trial, exactly. And you get access to not only to this training, but also to all books, to all the content of the platform, right? So if you're interested, you can scan this to get to the website, and of course, just ping me and send me a message, and I can give you further instructions for how to register. And then there is a second second course that I'm going to give in November 2021. This will be about advanced ontology engineering. So it's going to be 2 full days of 5-10 hours in total, deep dive into conceptual modeling problems and challenges, including meta-modeling, including vagueness, uncertainty, ambiguity, all these things, how to tackle all these enemies that we discuss, also extraction, quality, and etc. This is done in collaboration with Dataversity. I don't know if you know them.
Yeah.
And as I said, we did a very successful with Dataversity. I did last July a successful 3-day course on knowledge graphs and large language models, and we decided for November to focus most on the conceptual part of ontology engineering. Again, you can scan the QR code here to get more information about the syllabus, etc., and register. And again, feel free to ask me any questions about it. So, thank you very much. Yeah, I'm stop sharing and.
Yeah, thank you very much, Panos. Really enjoyed that. Any questions? Any questions for Panos? I'm just waiting for Jürgen. Jürgen, I know he's got a question. Jürgen, any questions from you?
Not today, Howard. Still thinking about this. This is an advanced topic, eh, Panos? But Marcel's got one. His hands up.
Marcel? Yes, Marcel?
Sorry. So how does LLM talk to AI?
Sorry?
What is the relationship between large language models and artificial intelligence? Okay,
great question. Subset. It's a technique. AI is a very broad term. AI is about creating applications that perform cognitive tasks that usually we attribute only to humans, right? Yeah. I think that's a very practical definition. Things like understanding a text, understanding exact information from text, classifying between categorizing things, understanding the sentiment of a movie, things like that, or recommending things are all under the umbrella of AI, in the sense that you automate something that so far only humans did, mostly with their mind rather than with manual things. So it's not about, it's similar to, in the 19th century, you had automation of manual labor, right? Of building things, more automation. Now it's more automation of cognitive tasks. That's the definition. LLM is, and generally, so there is various types of AI. LLMs fall into the field of generative AI. It's because of the way it's trained on. And LLMs is also a particular type of LLM, of generative AI, in the sense that it's based on text, on language. Because there are also
natural language. Yeah.
It's natural language, because there are also generative AI about music, about sounds, acoustics, music, and also about images and videos, video generation, etc. And nowadays, multimodal things. So, for example, with I think a version of GPT, you can generate me an image with that is like depicts, I don't know, a nice sunset in Santorini. So it will take the language input and will create an image. This is a multimodal example of.
And I think that's
knowledge graphs and semantic modeling, in my view, is also a subset of AI, which is symbolic AI, which was all the rage back in the 80s.
So does AI then use LLM?
Yes,
or is it
LLMs
it's a branch of AI, Marcel. So AI is the big they call it a briefcase term, which describes everything, and LLM's a tree, a narrower version of AI.
Of information that feeds into your AI.
No. So
Not really.
remember, LLM is a technique, an AI technique, right?
Okay.
There's no such thing as an AI.
Yeah.
There are applications, systems that do some things.
Yeah.
An LLM on its own does some things. When you are in ChatGPT and you're in the interface, you can do a certain subset of things.
Yeah. AI is a field of that we use to try to mimic cognitive behavior. That's the core.
Okay.
So
Thanks.
now you have lots of different techniques underneath that, from knowledge graph to LLMs to machine learning, all the different types that come about.
Reinforcement learning.
Yeah. Supervised, unsupervised.
Supervised, yes. Planning, many things.
Thank
So
you very
AI
much.
is the broad term that covers everything.
Yes, I understand. Thank you very much.
AI is an American marketing term. Right.
Yeah. I don't know, but yeah.
Yeah. Fantastic. Are there any other questions? Okay. Panos, thank you so much. I really enjoyed it. I really liked your way of checking what can be trusted and not, and where we should be wary. It was really great. Thank you. I appreciate it. And now the difficult question would be, and I suppose it's only really Marcel, because I bought the book anyway, so we don't have a hard choice here. Are you in agreement with that?
Yeah, I'm fine with that. Yeah.
Fantastic, Marcel. We'll Panos, what we've done with some of the other authors is that they are able. I'm not sure who. I think it's O'Reilly, but I'm not sure if we can get a signed copy. We wouldn't want to go physical because sending in the post is quite unreliable. Maybe we can sign an image and then we can ship it to Marcel.
I don't know. Yeah, I'm not sure. I haven't done it before, but if you have a way, yeah, I'm happy.
Okay.
Yeah.
Okay. Thank you very much.
Thanks, Howard.
Marcel, well
Thanks,
done.
Panos.
Panos, thank you so much, sir. Thank you so much, sir. Really appreciate it. Thanks to everybody. Have a wonderful evening. And yeah, I think Panos's training courses look great. I'll certainly look to join some of them. It will be great, Panos. Thank you.
Thank you.
Great.